One very important concept when talking about time series, and that has sort of popped up in some other videos in between the lines, is the idea of stationarity, and the opposite, non-stationarity. So stationarity refers to whether a time series has a long-term average, is moving randomly up and down with greater or lower levels of autocorrelation around some kind of average value, or it's more like a randomly walking around, like there's no average at all, it just can go anywhere. The strictly stationary distribution is one where the underlying probability distribution remains the same. The values might change over time, and there might be some level of autocorrelation therein, but it does vary around some kind of mean with some kind of variance. It has a particular distribution. Now, if we can just say that there's also something called weakly stationarity, which just focuses on those main features of the distribution. So the whole distribution might not be exactly the same over time, but there is a constant mean, there is a constant variance, and there's a constant covariance. The level of autocorrelation between current observations and previous observations does not change over time. Here's an example of a stationary process. It moves around, there's a relatively high level of autocorrelation, so if it goes high, it stays high for a bit, if it goes low, it stays low for a bit. But it does not go anywhere. Like, there is some kind of long-term average here at 0, so you could draw a straight line at 0, and if this time series goes on and on and on and on, it will always be revolving around this 0. Sometimes it stays for a while above it, sometimes for a while below it, it goes relatively up and down, but long term it keeps revolving around this 0. Well, here's an example of a non-stationary process, and if we drew a long-term line, we have no idea where it will go. Yeah, so it can go infinitely far up or down. There's no reason to expect it to revolve around the 0. So it can just go anywhere. There's no long-term average. We have talked about the concept of stationarity, where in a stationary time series, the time series revolves around some kind of long-term mean, and with strict stationarity, even the probability distribution across the time over time remains the same. So we can see the time series as sort of a random variation with autocorrelation within this distribution around this long-term average. And non-stationarity refers to a situation where there is no long-term mean and the time series just moves along, but the probability distribution is not around some kind of average. How we model our time series depends to some extent on the presence of stationarity. So most time series models, they assume stationary data, and when the data is non-stationary, then any kind of consistency or asymptotic normality of any of the estimators, OLS, ML, and so forth, they fail, because they estimate, the model estimates around some kind of constant configuration, structural pattern in the system, and when that structure is not there, then these estimates fail. So that means that as the sample size increases, you are not converging on the right estimates, and that is highly problematic. So we need to know whether there is non-stationarity in the data, and for that we need to test. Now, before we test, I want to explain the concept of the unit root, because that is what it's related to. If you have this regression equation that you see here, y at times t being a function of y at time t minus 1, and note that there is no coefficient for y t minus 1, so the coefficient is basically 1. This is the theoretical model here, right? So we're not testing this. But if this were the real model, if this is how yt is related to yt minus 1, so it is always just taking yt minus 1 and then some random variation, then it does not converge to any kind of average pattern. You can imagine, we talked earlier about shocks and how shocks dissipate gradually following some exponential function. In this equation, any shock to y never dissipates, right? Because the next iteration of y is fully dependent on the previous iteration. So any shock remains forever. And that means that it's non-stationary. And this parameter is 1, and that we call unit root. Now in this equation it's very straightforward, because there's only one parameter, time series parameter, and that is 1, and that's what we call the unit root. But unit root might very well be more difficult to detect. For example, the next example also has a unit root, but it's harder to see. Yeah, so if we have two variables that are non-stationary because they have unit root, and we regress them on each other, we have the spurious regression, which we discussed earlier. So it is crucially important to know that this is the case. So the most common test for non-stationarity is the Dickey-Fuller test. In the Dickey-Fuller test, we subtract t minus yt minus 1 from both sides of the equation so that we get a regression where the first differences are regressed on the lagged value of y. And then we have a coefficient here called beta, and we can test whether there's a unit root by testing whether beta is different from 1. Now note that the null hypothesis here is that beta is not different from 1, which would be the unit root. So you might have expected a test where the null hypothesis is no unit root and can we reject this null hypothesis, but instead we have a test where the null hypothesis is there is a unit root, and the question is whether we have enough evidence to conclude that there isn't. And I have not talked about integration yet, but the first differences are integrated of order 0, y is integrated of order 1 if the null hypothesis is true, and in that case we can the t-test itself is invalid. So separate critical values to reject or accept that the null hypothesis have been developed. Now the Dickey-Fuller test only works for AR1 processes, so that is a relatively limited set of processes. There is an extended version, the Augmented Dickey-Fuller test, which adds lagged versions of the first differences, and they are valid for higher order AR processes, ARP processes. We're still not talking about MA processes, we're talking about AR processes, but MA processes don't typically have a unit root. Note that the power is relatively low, partly because of what I said about the null hypothesis, so it detects unit roots quite easily. It needs sufficient evidence to reject it. And the power is a function also of the type and the strength of autocorrelation. Now, just like with other features of a distribution, for example, the mean or the variance, or we talked about bias, etc., they can have finite sample properties, but they can also have asymptotic properties that occur only when the sample size is sufficiently large. In time series, when it comes to stationarity, we can have what in a finite sample is a non-stationary time series, can, as time goes to infinity, as the sample size goes larger and larger, converge to a stationary time series. And we call this asymptotically stationary. So there is as the sample size gets infinitely large, infinitely many time periods, and the mean, the variance, and the level of autocorrelation in the time series starts to converge to a particular value, then we call it asymptotically stationary. And another way of saying that is that this is integrated of order 0. And we get back to integration in the next video. So a stationary process, if it's already stationary in a finite sample, it's certainly stationary when it goes to infinite, so it's always integrated of order 0. But a process can also be integrated of order 0, but not stationary in a finite sample sense.